A TLS certificate is like a digital ID card for a website. It proves the website is genuine and creates a secure, encrypted connection to keep data private between you and the site. Suppose you want to log into your online bank account. You enter your username and password. If this data is sent without encryption, anyone monitoring the network could see your username and password, allowing them to access your account. This is obviously not safe, and you must encrypt the data being transferred using encryption key. Data is encrypted using a key, which is a set of random numbers and letters before it's sent to the server. When a hacker intercepts this encrypted data, they just see random characters and can't make sense of it. However, the server also can't understand the data yet because it's still encrypted. To decrypt and read the message, the same key used for encryption is required on the server's side. So, this key needs to be transferred to the server as well. But here's the problem: if a hacker is still intercepting data, they might also capture the key during its transfer. With both the encrypted message and the key, they'd be able to decrypt the data and see the original message. This is called symmetric key encryption. In this method, the same key is shared to both encrypt and decrypt the data. This makes it less secure because anyone listening in could intercept the key and use it to read the message. This is where asymmetric encryption comes in. Instead of relying on a single key for both encryption and decryption, asymmetric encryption uses a pair of keys, a public key and a private key. The public key can be shared openly and is used to encrypt data, while the private key is kept secret and known only to the owner. It is used to decrypt data. The key distinction is that if one key is used for encryption, only the other key can be used for decryption. Returning to our previous example, the problem was that the key used for encryption also needed to be sent to the server for decryption. But the hacker sniffing the network can also get the key. What if we could transfer the key to the server securely? Once the key is safely available at the server, they can communicate with each other using symmetric encryption without any security concerns. To securely send a symmetric key from a client to a server, we use asymmetric encryption. This works by generating a pair of keys on the server, a private key, kept secret, and a public key, available to anyone. We have used OPENCIL commands to generate asymmetric key pairs. When a user connects to the server over HTTPS, the server shares its public key with the user's browser. Even if a hacker intercepts this public key, it's only useful for encrypting data, not decrypting it. The user's browser then encrypts a symmetric key using the server's public key and sends it to the server. Although the hacker can intercept this message, they cannot decrypt it without the server's private key, which remains secure on the server. Now, both the server and the client have the symmetric key, which they can use to encrypt and decrypt data back and forth securely. The hacker, having only the encrypted messages and public key, cannot read or alter the data. By combining asymmetric encryption for securely sharing the symmetric key and symmetric encryption for efficient data exchange, we ensure secure communication between the user and the server. A hacker could try to steal your credentials by creating a fake website that looks exactly like your bank's site. They replicate the design, graphics, and everything else, hosting it on their own server. To make it seem secure, they generate their own public and private keys and configure them on their fake web server. Then, they trick your environment or network to redirect your requests from the real bank's website to theirs. When you type in the bank's web address, you're shown what appears to be a familiar page. Confident, you type your username and password, thinking it's secure because you see HTTPS in the URL. Your browser receives a public key, which you use to send an encrypted symmetric key and eventually your credentials. You're communicating securely, but with the hacker's server. As soon as you enter your details, you're taken to a fake dashboard. Now, what if you could verify the authenticity of the key you received? When a server sends a key, it doesn't send the key alone, it sends a digital certificate that contains the key and other information. If you check the certificate, it includes details like who issued it, who it's issued to, the server's public key, and location. On the right of the certificate, you'll often see the name of the person or entity the certificate is issued to, known as the subject. For a web server, this must match the URL typed by the user. If the entity has multiple valid names, those should appear under the subject alternative names section. However, anyone can generate a certificate saying they're a legitimate organization. The hacker, for example, could create a certificate claiming to be your bank. So how do you determine if it's authentic? The most crucial part of a certificate is who signed it. When you create a certificate yourself, it's self-signed. Anyone reviewing the certificate can see it was signed by the creator, not a trusted authority. Browsers help with this by checking the certificate's authenticity. If they detect a fake certificate, they warn you. To make a certificate that browsers will trust, you need it signed by a certificate authority, CA. Trusted CAs, like Symmetric, DigiCert, Komodo, and Global Sign, verify your identity and sign your certificate. You generate a certificate signing request, CSR, using your key and domain name. This command creates a CSR file, which you send to the CA for verification. Once approved, the CA signs the certificate and sends it back. Now, you have a certificate signed by a CA that browsers trust. If a hacker tries to get a certificate signed in the same way, the CA would reject their application. So, if the hacker hosts their site, it would lack a trusted certificate. CAs use verification techniques to ensure applicants are the legitimate domain owners. Browsers also verify the CA itself. CAs have their own key pairs, and they use their private key to sign your certificate. Browsers have a built-in list of CA public keys and use these to verify CA signatures, ensuring the certificates are authentic. For private sites, like internal company resources, you can set up a private CA. You deploy the CA server within the company and add its public key to employee browsers, enabling secure, authenticated access to internal applications. Thanks for watching. If you found this breakdown helpful, hit the like button, share this video, and subscribe for more DevOps tutorials and tech explanations. See you next time.